All right, if you're prepping for NEAT, you know this chapter is going to show up. So today, we're cutting right to the chase. We're going to focus only on the highest yield concepts from mechanical properties of solids. Let's zero in on what's actually going to get you those marks.
So think about it for a second. Why does a rubber band stretch like crazy, but a glass rod just snaps? This isn't just a random question. It's literally the core of this entire topic. And the answer? Well, it all boils down to how different materials handle two fundamental ideas. And those two big ideas are stress and strain. Seriously, every single concept in this chapter, from how elastic something is to its final breaking point, is built on the relationship between these two. So let's break them down one by one. Okay, let's start with stress. Imagine you're pulling on a wire. Inside that wire, it's pulling back, right? It's resisting that change. Stress is the measure of that internal fight, that restoring force, spread out over its area. And the formula, you see it right there. It's just force divided by area. It's the material fighting back. And what's the result of all that stress? Well, the wire deforms. It stretches out. We call that deformation strain. It's really simple. It's just the change in length compared to its original length. And here's a key point, a classic MCQ trap. Since it's a ratio of length over length, strain has no units. Lock that piece of info away. So how do we connect the internal fight, stress, with the external change, strain? The bridge between them is this thing called Young's modulus, or Y. You can almost think of it as a material's personality. Something with a high Y value, like steel, is super stiff. It takes a ton of stress to make it strain just a tiny bit. It's all about how much a material resists being deformed. Okay, now let's see how this all plays out visually. This next slide shows the stress-strain curve. And I'm not kidding, this is probably the single most important diagram in the whole chapter. If you can learn to read this graph, you can solve most of the conceptual questions they'll throw at you. This curve basically tells the life story of a material as you pull on it, so follow along with me. From point O to A, see how it's a perfectly straight line? That's the proportional limit, where Hooke's law is king. If you release the force anywhere up to the elastic limit, point B, the material just snaps right back to its original shape, no problem. But if you go past point B into this curved section, you've done permanent damage. This is the plastic region, and the material will never be the same again. And that first part, that predictable straight line, it's all governed by one famous rule, Hooke's law. It's as simple as it sounds. Within the elastic limit, stress is directly proportional to strain. A huge number of NEAT numerical problems are designed to test you on just this simple linear relationship. But what if we just keep pulling? We go way past the plastic region. Well, every material has a limit, a breaking point. And that's what we're looking at next, the ultimate tensile strength, or as we call it, breaking stress. Now, this slide has a golden rule for your exam, so pay close attention. Breaking stress is an intrinsic property. That means it depends only on what the material is made of, like its color or density. It has absolutely nothing to do with how long the wire is or how thick it is. Let's see if you've got that with a classic trick question. Okay, here we go. Picture this. A wire can hold a maximum of 15 kilograms before it snaps. Now, if we take that same wire and cut it into 4 shorter pieces, how much weight can one of those smaller pieces hold? Take a second to think about it. The answer is still 15 kilograms. If you thought it would be less, you just fell for a very common trap. Remember the rule we just talked about? Breaking strength is about the material, not the dimensions. Cutting the wire doesn't change what it's made of, so its strength stays exactly the same. Don't let them trick you with that on exam day. All right, theory is one thing, but let's be real, NEAT is all about applying it. So let's tackle a typical numerical problem you might see. This is where we put these concepts to the test. So here's the setup. We've got 2 wires, A and B. They're made of the same stuff, they're the same length, and we're pulling on them with the exact same force. The only difference is their thickness. Their radius are in a 2-to-1 ratio. The question is, which one stretches more and by how much? Let's find out. To solve this, we need our main tool. We just take that Young's modulus equation and we rearrange it to solve for what we're looking for, elongation, or delta L. As you can see, the stretch depends on 4 things: the force, the original length, the cross-sectional area, and the material's Young's modulus. Let's walk through this logically. Step 1. What's the same for both wires? The problem tells us force, length, and Young's modulus are all constant, so we can pretty much ignore them for the comparison. Step 2. So what's different? just the area and the elongation. Step 3. Now look at the formula. Elongation is inversely proportional to the area. That means if the area gets bigger, the stretch gets smaller. Step 4. Let's figure out the area ratio. Area is pi r squared, so it's all about the radius squared. Since wire A has twice the radius, its area is going to be 4 times bigger. And finally, step 5. If the area is 4 times bigger, that inverse relationship means the elongation will be 4 times smaller. So the final ratio of the elongation is 1:4.
Done.
So to wrap it all up, this entire chapter really just boils down to this one fundamental difference. Elasticity is like a spring. It always bounces back. Plasticity is like a piece of clay. You push it too far and it's changed forever. That's the whole game. And I'll leave you with one final thought. Knowing the formulas is just one part of it. The real understanding, the kind that gets you top marks, comes from intuition. For a bridge cable, you want extreme stiffness, right? You want it to stay deep in that elastic region. But for a car's shock absorber, you actually want it to deform and absorb energy. Think about why we choose certain materials for certain jobs as you keep revising. All right, good luck on the exam.